Hi, this particular lesson, we're going to combine a lot of things all together at once. For one, we're going to be implementing this informed speculative approach to try to figure out what's going on before we charge off and do a whole lot of work, which with flexural deformations, that oftentimes is the case. It's a lot of work. And we're going to be applying these models to indeterminate systems. And that's one reason why that it's a lot of work, not just because it's associated with flexural deformations, right? And you're going to find out when you do this stuff, it's going to be hard. It's going to be time consuming. It's going to involve a lot of things going all on at once. You're going to want to get some extra help, and then you're going to go out there on the web and try to find other approaches for these indeterminate systems, and all of a sudden you're going to come up with a whole bunch of different names. So we'll talk about what some of those different names are. They're all the same thing. In fact, let's just do it right now. You got the relaxation method. You have the method of consistent deformations. You also have what's called the flexibility method. And the same thing is encompassed by the name the force method. Four titles, all emphasizing a different kind of aspect of what's going on. And that's why we have different names. But it's all the same. So once again, that's the, I don't, not in the same order, but the method of consistent deformations, the relaxation method, the flexibility method, and the force method. The force method is so named that because in the calculations that we're doing, we have excessive or redundant reactions, which, oh, by the way, is another name for it, redundant reactions, right? So more reaction components than we have equations of equilibrium for, and so we end up writing additional equations, which happen to be a displacement equation. That's why it's called method of consistent deformations, where the unknowns in the equation are the reactions or forces. Hence, it's called sometimes the force method, right? And by the time we get done with this, there will be a very specific process that we'll follow. We'll review that. And overall, though, we're going to be using this approach to solve 1-degree indeterminate systems. We can do it for an infinite number, although it'll take us infinitely long. In that case, it takes a long time if you have a lot more redundancies to have to deal with. Okay, so that's the big picture in some sense of what we're about to charge off and do. Okay, so keep note here, the nomenclature in terms of example numbers are going to be a little off. What you have in your study notes as example FD 2.2, there's the one that's shown on screen here is actually 2.4. There was I've had a lot of different kinds of questions over the years. This is actually a statically determinate system. And students asked me to give them another example with a hinge. It showed up here at the end of this lesson packet. So you'll see different nomenclatures, but when you see the beam with a hinge and it's a determinate system, that's the one that's going on with that particular number. All right, let's get into it here. We have a two-span bridge that a DOT in the northeast of the U.S. wants us to help them with, right? And so it's your typical 4-lane highway that has 2 lanes on each side and divided or a median down the middle. We've got this hammerhead concrete pier in the middle that is our support. We have then all these pre-stressed concrete girders that are running along and supporting the deck, which is also integral to it. And then we have the 2 abutments out here on either end. In this case, an equal span situation. This little drop down lighted gray box that you see at the middle and at the left are actually the downspouts for the water that collects on the surface of the roadway above and then drains to that spot and then comes down. They put that downspout so that that water will presumably not drip onto the structure, but rather will fall to the ground and not create potential corrosion issues associated with the superstructure. All right, so we're in the Northeast, and in the Northeast, the New England bulb T girder is pretty common, and that's what the DOT has requested us to use. To get some quick estimates of what we might be dealing with here, we are going to simplify our model down to here we've got this 2-span continuous beam. We've got a uniform load. We can look at the moving load aspect later, as well as asymmetrically placed live load another time. Right now, we're just looking at full on dead, full on live in a static kind of position. And we recognize with all the symmetry that's going on that we really don't have to analyze the entire beam, that there's a reflection line or a mirror line right down the center. And we can simplify our model then as such. We got a 35-meter span on the right and also on the left, but the one we got shown here is on the right with a tributary load that includes the way that the concrete deck then shares its load amongst companion or parallel girders at a load that's 29.2 kilonewtons per meter. That's what we're going to go try to find reactions for, and then find the shear moment diagram and the deflected shape that goes along with that.